Yeah, so after we've looked up the way to do matrix multiplication, the next operation that we need to look up is what is known as the transpose of a matrix. And this is pretty easy. Basically, all it means is that you're flipping the rows for the columns and flipping the columns into the rows. If you write it more formally, let's say your original matrix is A equals Aij m by n, then your transpose is written as A transpose or A prime, whichever you prefer. It becomes Aj, again m by n, or n by m, sorry. So you're flipping the rows and the columns. A quick example, so if you start off with something like A is 3, 4, 5, 9, 8, 7, then I personally prefer the AT notation to denote the transpose. So you're flipping this row becomes this column, so 3, 4, 5, and then this row becomes this column, so 9, 8, 7. Pretty easy. Now before we move on, we need to look at some special properties of the transpose operation. So some of the easiest ones. If you take the transpose of a matrix and take its transpose, you get back the original. So like right here, we flip the rows into the columns. If you do this again, you'll get back the original matrix. The second property, if you have an addition of matrices, so A plus B transpose, you can do A transpose plus B transpose. Third property, if you have a product of two matrices, AB transpose, the order of the multiplication becomes flipped in the transpose product. So it's B transpose, A transpose. And in general, if you have something like A1, A2, AN transpose, that will become AN transposed times AN minus 1 transposed, product all the way to A2 transposed, A1 transposed. And then for a special case of a square matrix, that is if M equals N, if A equals A transpose, then the matrix is called symmetric. So for example, if you have a matrix like then you can see that by flipping the rows and the columns, you have A transpose is again the same thing basically. Which is equal to A. Now we come to what is known as the determinant of a matrix. So what is a determinant? Up until this point, we've been studying matrices in general. So again, to recall, a matrix is an ordered rectangular array of numbers. So like we saw in the example with the cricket scores, it's simply a method to represent a lot of data. It doesn't have a value. So if I give you this matrix, for example, and tell or ask you, well, what is the value of that? You'll say it has no value, it's just a representation of numbers. But then for a special class of matrices, it's called square matrices. If A equals Aij n by n, or is this general matrix where m equals n, then you have a value of that matrix which can be determined. And the way to determine that value is the determinant of the matrix. So that is the value of the matrix. And the thing to remember, only square matrices can be assigned a value. Not every general rectangular matrix has a value. So a simple case, let's say A equals this matrix. So it's a 1 by 1 matrix, the number 7. Then what is determinant of A? Well, as you may guess, it's just one number, and that is the value of the matrix. And the way to write the determinant in shorthand notation is in between these two vertical lines. This symbol represents the determinant of a matrix, and for this simple case, it's just the number 7. So this is what is called as a first order determinant. And then we look at the second order determinant. As you may guess, it's a determinant which has a 2 by 2 structure. Or starting off with the most general 2 by 2 matrix, A11, A12, A21, A22. It's a 2 by 2 determinant, 2 by 2 matrix. Then determinant of A, again represented as this form. So you would write it as A11, A12, A21, A22. And by definition, this is calculated as A11 times A22, so the product of these two elements, minus A12 times A21, so the product of these two elements. And we'll see where this comes from in the more generalized case. But for now, it's important to remember that for a 2 by 2 determinant, the way to calculate or to determine the value of the matrix is you take the cross product of the diagonal elements, and from that you subtract the cross product of the non-diagonal elements, and that gives you the value of the determinant. Moving on to a third order determinant. So the general case would be A equals, this is a big thing to write, but A11, A12, A13, A21, A22, A23, A31, A32, A33. And continuing on this side, the way you calculate the third order determinant is interesting. You write it as this form. So what you will notice here, this is a 3 by 3 determinant. These are the rows of the determinant, and these are the columns of the determinant. And to determine the value of this determinant, you can expand it by any row or by any column. And without loss of generality, let us try to expand it by the first row. And for now, you will have to take it from me as a definition but the way to calculate the value of this is A11 times another determinant, and the times this determinant, you find this by mentally blocking off this column of which A11 is a part and blocking off this row of which A11 is also a part, and taking the rest of the original determinant. So that gives you A22, A23, A32, A33. So that is the first term of the expansion. Then a minus sign, the second element, A12. So again, mentally you would block off this column because A12 is a part of this column, and you would block off this row because A12 is a part of this row, and take the rest of the elements. So A21, A23, A31, A33. And the third element has a plus sign. The third element is A13. And again, by mentally blocking off this and this, you get A21, A22, A31, and A32. And so the final answer for the expansion of the third order determinant is this product. So A11, A22, A33 minus A23, A32. How did we get this? Well, using the second order definition. So for the second order, as you remember, it's the product of the diagonal elements, and then from that you subtract the product of the non-diagonal elements. So that's what we did here for the first term. A22 times A33 minus A23 times A32, and similarly for the other terms. And where this minus sign came from, we'll see when we get to minors and cofactors of the determinant, but for now you'll have to take it as the definition. So A21, A33 minus A31, A23 plus A13 times A21, A32 minus A31, A22. Okay, so that's a big multiplication, and as always, let's take an example to make this clearer. So let's start off with a simple example of a second order determinant. So let's say someone gives you that this matrix root 2 minus 5 minus 5 0, and asks you, well, can you determine the value of this matrix? So the way to do that is you write determinant of A as 2 minus 5 minus 5 0, and then using this operation, so the value of this determinant is root 2 times 0 minus minus 5 times minus 5. So the value is minus 25. For a slightly more complicated case, let's take an example of B equals, I'm straight away going to write the determinant. It's coming from its matrix. Let's take 1, 2, 3, 4, 5, 6, 7, 8, 9. And so to find the determinant of B, again, let's expand by the first row. So starting with the first element 1 times, you mentally block off this column and this row, so you take the rest of the matrix. So that is 5, 6, 8, 9 minus the second element 2, and you block off this column and this row, so you are left with 4, 6, 7, 9 plus the third element, which is 3, times block off this and block off this, so you're left with 4, 5, 7, 8. And and continuing down here, so the first term is 1 times 5 into 9, so 45 minus 48 minus 2 times 36 minus 42 plus 3 times 32 minus 35. And so the value of this determinant comes out to be 0. And that is the step-by-step way to calculate the value of a third order determinant.